everyone. Here we're talking about mechanical advantage. It's the way that your bicycle, if you've ever geared down your bike to ride up a hill more easily, that's mechanical advantage. If you've used leverage to move something heavy, that's mechanical advantage. Or if you've used compound pulleys, it's mechanical advantage. Sorry, we're not going to call that 100. It's 100 newtons. 100 newtons. Okay. So the way to spot whenever you've got this kind of these coupled pulleys, what do they call them? Compound pulleys, is when you have multiple different cables involved. So this, as you can notice, isn't a single cable snaking through all these pulleys, but there's one that connects that goes around pulley A and ends at the pin of pulley B. There's another that goes around pulley B, ends at pulley C, and then there's this third that goes through pulley C and D and ends at this tension P that we're going to try and find. Okay, so if we've got a 100 Newton load hanging off of pulley A, let's just start there. So it's 100 newtons. These are both TA, like me. Okay, so 2 TA minus 100 newtons equals 0. So we get the TA is 50 newtons. Easy enough. Likewise, that was pulley A. We go to pulley B. We see here we got B, and now, since this came off of pulley A, which we found to be 50 newtons, our load down here is only 50 newtons. And so then TB is going to be equal to 25 newtons. Pretty easy, right? And so we see that, the more and more you go on with these, you're just going to keep having the amount of tension it takes in the cord to create equilibrium. So then we go to pulley C. Just draw it here, pulley C. So we've got 50 down here. Sorry, 25 down here. And so you tell each of these is going to be 12.5. Okay, so that's 12.5 coming off of here, which goes around D and is the same as P. So we got our answer, that P is 12.5 newtons. And so notice that it would have taken 50 newtons tension here on A to hold up the 100 newtons, because you got 2 times 50. And it's taken 25 newtons on each to hold up B. It's taken 12.5 to hold up C, equivalent on D because we're in the same tension. You get down to there. So just note that whenever you see multiple different cables running through a pulley problem, you gotta look out for this mechanical advantage. It should all come out in your free body diagram, but that's how you know. Alright, so in this example, this is problem 666. We're going to be looking at the way that you have to treat moment around pulleys when you're trying to find, some equilibrium or free body diagram, the members of frames and stuff like this. So this question just wants us to find the support reactions at A and D. So these are both pin joints, so we're probably going to be seeing, dx, dy, and going to calculus, sorry. A dx, a dy, an ax, and an ay component, all right? And so what's interesting here is that we've got our pulley C that's supporting a pulley E that's supporting a 12 kilonewton load. And so we only have this one single cord going from C around E and then back and hooking into the wall here. So in order to find our AX and AY components and then ultimately DX and DY components as well, we're going to need to know how these forces around here are playing into the free body diagram of this member from A to C. And so what we should do first is let's take a look at pulley E. So E's got this 12 kilonewton load it's supporting, which means you've got 6 kilonewtons tension which is in both of these. So that 6 kilonewtons is all the way around here, okay? And so if you look further up at pulley C, then you're just going to have 6 kilonewtons here and 6 kilonewtons there. And now normally when we see this kind of thing, we just automatically say, okay, so then the pin is supporting this, you know, we'll call that CX or CY if we wanted to. But the thing to note here is that, you know, E is still pulling down on member AC, as is, you know, this part of the pulley. It's splitting up this 12 kilonewton force, and instead of just applying it at this one point, now half of it is applied here and half of it is applied here. So if we want to look at our free body diagram, we have half of our 12 kilonewton load applied right there at the joint, at the pin, so that's 6 kilonewtons. But then the other half is going to be, it gave us that the radius was 0.3 meters on this. So you go 0.3 meters away, call that 0.3 meters, and that's where the other 6 kilonewton load is. And so this is important, right, because it's going to factor into the way that we do our equilibrium equations, because that's going to create a slightly different moment than this. Similarly, we have this other 6 kilonewton load that's 0.3 meters above, that's pulling back in, that we saw here. Right, and so that's 6 kilonewtons. Okay, and then we've got our AX and our AY. And then we have our FBD, we'll call it. And note that FBD is a 3-4-5 triangle. Yeah, with 4 on this one, 3 and 5. All right, so with that, let's just go ahead and get to solving. So let's start out with that moment, all right? So summing the moments counterclockwise about A. We have, all right, this was 1.5 to here, and this was 1.5 to here, so it's 3, right? Sorry. This is 1.5 meters, and this is 1.5 meters. Apologies. All right, so we get 6 kilonewtons times, and these are twisting it clockwise, so let's go negative. Negative 6 kilonewtons times 3 meters, and then minus 6 kilonewtons times 3.3 meters. So that's this one. So 6 times 3, 6 times 3.3. Okay. And then, trying to turn it counterclockwise, we have another 6 kilonewtons that's only 0.3 away from our axis of rotation, right? So then we're going to add another 6K, this time times 0.3. All right, and then plus the Y component of our FBD, which is going to be 4/5 of FBD. All that's going to equal 0, and what you end up with is that FBD is 30 kilonewtons. Yeah. All right, cool. And now it's just your simple summing of the X's and Y's, like you know all too well by now. So X's, you've got minus 6 kilonewtons minus 3/5 of 30. Which is, what, 18? So that's minus 24. So we get AX equals 24 kilonewtons. Okay. We'll do the same in Y. We've got minus 6 plus 4/5 of 30 which is 24, plus AY. Well, let's see, that's actually going to be a minus AY, I suppose. Well, we drew it in the plus, so let's keep that as plus AY. And then that's going to get us that AY is minus 12 kilonewtons, because we drew it in the positive direction, so we could just flip that around and say that 12, it's positive 12 in the negative direction. Y'all get it. All right, and so that's our AX and our AY. And then from there, you just have FBD, which, if you'll notice, pin joint, it's a 2-force member. And so if it's 30 kilonewtons going like this here, then up here we've got 30 kilonewtons going down. And so 3/5 of it is going to be your dx, 4/5 is going to be dy. So dx is going to be 18 kilonewtons. And dy is going to be, it'll be 24. All right, so this problem 667 is a kind of interesting one. You might want to look at the diagram for a little bit clearer picture, but basically this A all the way to B is just one continuous member, and then B up here curving around to C is the other continuous member. So this frame is just the one, a pin joint here, and then a solid D that has this 90-degree turn in it. And then it's on this little roller here between this wall, and it's on a pin over here. And it's so this is floating right here with respect to the wall. It's just this roller at D that's keeping this there. And then we've got a 60 pound-foot torque moment being applied clockwise at point A, and it asks to determine the force that smooth roller C exerts on member AB. So member AB here, member C here, the smooth roller. So if y'all remember, a smooth roller, just like little rollers you see underneath the truss or whatever, the only reaction force generated by this, since it's smooth, there's no friction, is just going to be this normal component right here. We'll call that FC, and that's what we want to get. I don't know why I circled that. It kind of looks like another roller. All right, that's FC, and that's what we're after. Okay, so it's this weird thing where it's turning this, which is causing that arm to wanna eat, like to push back into it, which it's doing at C. So basically, this turning at A is causing this member that goes from BDC to push down here. And so we're trying to figure out what that force is right here. Okay, so it's a weird looking problem, but it's pretty simple because there's only one support reaction, and that's going to be this smooth roller at point B. And since it's a smooth roller, again, point D, excuse me, it can only have that normal component, which in this case is going to be called dx. Okay, so those are our only two support reactions are at the pin here and at dx here. We haven't been given any of the ax or ay, but we have our 60 pound-foot moment. And so what we can do is just go ahead and sum moments about A. So, and counterclockwise. And so we get minus 60 plus whatever dx ends up being. And that's 0.5 away from A, right? Because you draw it out and it's just going to be 0.5 away from A. So minus 60 plus dx times 0.5 equals 0. And that gets us the dx is 120 pound-feet. Okay, So now we know dx. That means we can get ax if we want to. We really don't have to, but that sort of is the order you'd want to go in anyway. So summing in the x's, we get that dx minus ax equals 0. And so ax equals dx equals 120. Okay, but what we're really here for is this, whatever this force is going to be here. So how are we going to get that? We don't have any y reaction forces. There's no ay, there's no dy. But we're trying to get this in the vertical component. And whenever that's the case, we're going to want to look to moments again. We already summed our moments about A. There's nothing left it can do for us. And then there's only one joint left in the problem, and that's this guy right here at joint B. So if we sum our moments about B, what do we have? Well, we have dx is 120 pound-feet, 0.5 away from point B. So that's rotating it counterclockwise, which is positive. So we're going to say 120 times 0.5. Okay, and what's going to be counteracting that? Our normal force from our roller pushing down on this. So that FC is 4 meters away from B. So we subtract FC times 4. It's all going to equal 0. And we get FC is 15 pounds. Not pound-feet, right? Because it's just a normal force. And so this weird kind of like I don't know. I don't even know how to describe it. But this silly little thing. It's actually a really pretty easy problem. You just have to see what's going on here. You see there's only these two members that you can worry about. You have this, start out with only being given a moment. You realize that you can sum the moments about A using this support reaction dx. Once you have dx, you can sum the moments about B, and that'll help you find your FC. Alright, problem 655 is from your homework. We're going to be doing method of sections with space trusses. So you know it's going to be a whole lot of fun. So it wants us to find EF, AF, and DF. So it's going to be this guy here, this one here, and this one here. So we're probably going to be making a little cut around here. However, before we can do that, we will need to find our support reactions. Now, there's support reactions on joints D, A, B, and E. And remember that in these space truss problems, whenever they show you that little like kind of little rocket looking thing, it's supposed to be a ball and socket joint. And when it's directional like that, when it's offset from where the truss is coming together, that means it's only along that direction that you're going to be able to get you're going to be able to have support reactions. It's the roller equivalent in 3 dimensions. So what we have then is, these are the initial loads that we have. There's a dx, there's a dy, and I'm just drawing these arrows like this. If they're wrong, it'll come out in the equations and we'll be able to flip them. We have ax, ay, my bad. All right, let's write that down as we go. We've got dx, got dy, dz. Oh my goodness. Got dz. All right, we've got ay. B has both z and x. Call that bz. Call that bx. Call this one ex. Okay, and so to solve for this, we can do all 3 of our forces and all 3 of our moments. and get to figuring it out. So let's get on it. So in the x, looks like we have dx, bx, ex, and 2 kilonewtons. Let's go 2k plus dx minus ex minus bx. And now remember, I know these have different signs. It's just because I drew them this way. If that turns out to be wrong, it very well could be. We'll find out. So that equals 0. Can't do anything with that yet. All right, let's take a look at y's. We've got 3 kilonewtons in the negative y direction, and then we've got ay. So we have ay minus 3 kilonewtons equals 0. Well, that's solvable. So we know that ay is 3 kilonewtons in the direction that we drew it. So that's nice. Okay, moving on to z. We have bz, dz, and 4 kilonewtons. You can tell already, since that 4 kilonewtons is up, and I drew both of these upward, one of them, at least one of them, is probably not going to be in that direction, but we're just going to go ahead with the convention we've done. 4 kilonewtons plus dz plus bz equals 0. Can't do anything with that yet. All right, got to move on to moments. All right, y cross z is x. X-axis, y to z. Means x, this one, counterclockwise, is going to be that way. Into the page, kind of. Into the page and off to the left. All right, so what's going to do that? 3 kilonewtons. It's going to do that. That one is applied. 3 kilonewtons. These are 60-degree angles because it's 3, 3, 3. So that's going to be 3 kilonewtons times the sine of 60 degrees. So 3 kilonewtons times 3 is the length of the arm. Okay, so it's 3 times 3 sine 60. Okay, it's going to be that one. And then we have dz is pushing us the other way, so that's going to be minus. So I have minus dz times, that's 3 meters. Should be better at putting meters on these before. All these lengths are 3 meters, and then the long one is 5. All right, so we've got 3 times 3 sine 60 minus our dz times 3. All right, and we also have 4 kilonewtons, which I drew incorrectly. All right, we also have 4 kilonewtons creating a moment about the x-axis 1.5 meters away. That's cosine 60. And that's also counterclockwise, so we're adding that. Plus 4 times 1.5 equals 0. So this actually does isolate a variable. We can solve for dz, which we get 4.6 kilonewtons. Okay? Then if dz is 4.6, sorry, I had that wrong before, guys. So minus of that, then bz is going to be 3 minus 0.6 kilonewtons. All right, moving along, we've got a moment about y. Okay, so moments about the y-axis, that's going to be sticking out here, so our counterclockwise is like so. And so it looks like EX, this 4 kilonewtons, this 2 kilonewtons, DZ, and I think that's it. Yeah, all right, so we've got EX, that's going to be 3 sine 60 away from the y-axis, so we've got minus EX times 3 sine 60. Okay, 4 kilonewtons, that's going to be 5 meters away from the y-axis, and it is rotating us positive. So plus 4 times 5. Okay, 2 kilonewtons, that is also rotating us positive, and that is 3 sine 60 away from the y-axis. 2 times 3 sine 60. Okay, and what was the last one? dz, okay, which is going to be the opposite sense of minus dz, and that's 5 meters away as well, times 5. Okay, we found dz to be 4.6 kilonewtons. So if we sub that in, we will get our EX, which is 0.85 kilonewtons. Alrighty, one more. Okay, in the z direction, what do we have? So we've got EX turning it clockwise, 1.5 away. Okay, we have, that's in the z, we have 3 kilonewtons turning it clockwise, counterclockwise. No, clockwise. 3 kilonewtons clockwise minus 3, and that is 5 meters away. Yep. Okay, we have 2 kilonewtons 1.5 meters away, turning it counterclockwise, so plus 2 times 1.5. Okay, we have dx 3 meters away. That's 3 meters away from the z-axis. And have ay. There we go. Ay, 5 meters away, turning clockwise. All right, so plus ay times 5. All right, we already know ay. We already know ex. Let's just solve for dx. What we get for dx is minus 0.58 kilonewtons. Okay, so that means we drew our dx backwards. We're just going to leave it as minus 0.58 and leave our free body diagram how it is and just carry on with the problem. And having all of this, we can go back up top because we have our dx and we have our ex. We can solve for bx now. And what we get for bx is positive 0.5758. We'll call it 58. Yeah, bx and dx are equal. All right. So now that we got our support reactions, we can actually go ahead and do the problem. I'm going to go up here for that. So what we want is FEF, FAF, and FDF. So we can cut up here, but what we see is that up here we don't know any of these four members yet. And what we can see actually is that if we're trying to get DF, we can look at the equilibrium at joint D here, and it's going to be real easy because if we look at joint D, we have dx, this is minus 0.58. We have dz is 4.6. All right, and so we can forget about this because that's going to be in the x direction. We don't have any x component to member DF. And so we can just set the z component of DF equal to this 4.6 kilonewtons. And we can already tell that it's going to be in compression because it's got to push against that 4.6, pushing up, right? So that's FDF. So right now we're basically looking in you know, 2 dimensions with the z-axis here, the y-axis here. Okay, so if we just sum in the z, this is at joint D. All right, summing in the z, we get this 4.6 kilonewtons minus FDF sine 60 equals 0. And we get FDF equal to 5.31 kilonewtons. Okay, that's one of our answers. All right, and so now we can move on up to joint F because we have 1 known, 2, 3, 4 knowns, and 1, 2, 3 unknowns. Okay. All right, and so now finally moving on to joint F. We can use our summations in x, y, and z to figure this one out. And those of you who have done this already, should be most of you because it's on the homework, will have found that this turns out to be a zero force member, FCF here. And as far as I'm aware, by inspection, we can't just throw that FCF out immediately, and that's because even though C doesn't have any external or support reactions going on in it, we see this dx right here. So it's going to have to get, you know, there's going to be this tension here in CD counteracting that. Okay, and so that means that either component CA or component CF, or both, are going to help counteract that tension that's going to be in this member here, because there's nothing from either of these two members, DF and DA, that would be able to counteract that X. So we know it's going to have to be through one of these. So we can't count CF out by inspection as far as I'm aware. But the good thing is, if you're ever not sure about a zero force member, you can just do the math and see if it should be in there. All right, so we're going to go ahead and sum about X. So we have 2 kilonewtons this way. We have our FEF here directly opposing it, and then we have this component of FC. All right, so it's going to be 2 kilonewtons minus FEF. Okay, minus, this is 5 by 3, so that is going to be root 34. Yeah, so it's going to be 5 over root 34 times FCF. That's 0. All right, let's go look at Y. In the y direction, we've got minus 3k, and we've got a component of CF and this component of AF. So we have minus 3 kilonewtons plus 1 point, well, the FAF times the sine of 60, cosine of 60, excuse me. Okay, we're going to add our compressive load, our FDF, which is 5.31 kilonewtons times the sine of cosine of 60. Alright, and then finally minus this component of our big weird triangle we did, which is going to be FCF times 1.5 over root 34. And that all sums to 0. Okay, finally RFZ. We get our 5.31 from FDF kilonewtons sine 60 this time, minus our 4 kilonewtons minus our FAF sine 60, and finally this component of our funny triangle, which is going to be 3 sine 60 over that root 34. So minus our FCF times 3 sine 60 over root 34 equals 0. Alright, this is one big system of equations. You go ahead and solve that, and you end up with FCF is a zero force member. If anybody can say for certain that's zero force by inspection, let me know and I'll update people, but I'm pretty sure you have to keep it in for not knowing whether or not, unless you had done some other analyses at other joints. But this is method of sections, mind you, so we're just trying to do as little work as we can, which is just, this half-hour problem. There shouldn't be this much solving in a truss problem on a test. All right, most likely. You'll have a lot of time to do it if there is. So FCF turns out to be 0. FEF is 2 kilonewtons in tension. And then FAF is 0.69 kilonewtons, also in tension. And that's the whole problem. Okay, I know I kind of glossed over these weird root 34 things, but basically this component, this member here, CF, that triangle that it makes on the face of this prism, if I just drew the triangle out like this, it would be this 3, 5. So then, this is the square root of 5 squared plus 3 squared, which equals the square root of 34. And I actually do kind of like that they solved it like this, because then you have your proportions, and from there you can go about using your sines and cosines when you need to. So for example, in the z direction, this 3 sine 60 over the square root of 34